This is Unit 3, Section E. We're working on optimization problems. And we're starting on this one with example 7. We have an aluminum can that needs to be manufactured to hold 1,000 cubic centimeters, or 1 liter of juice. And we'd like to find the dimensions of the can that use the least material. So essentially the most effective way of building this can. Least material used would be less cost, right? All right, I'm assuming here this aluminum can is a typical cylindrical shape. And the amount of material that goes into making this cylinder, this can, is actually going to be the surface area of the cylinder. So if I assume that my cylinder has got a radius of r and a height of h, then the surface area, or amount of material that this is going to take, is 2 pi r squared. It's the two circles, top and bottom, plus 2 pi rh, which is the lateral surface area around. Again, that's on your list of formulas if you need it. And as is typical, we've got the problem that we've got too many variables, both an r and an h, and I can't take a derivative until I get it down to just one independent variable. So this is my, oops, I didn't label it this time, but this is my objective function. I'd like to minimize the surface area. And since I do have too many variables, I'm looking for a constraint. Once again, I'm going to look back and say, hey, what more information do I have that I might be able to use? And in this case, we know this needs to hold 1,000 cubic centimeters. So I'm going to use that information to create a constraint. The 1,000 cubic centimeters would be the volume. So the volume has to be 1,000. And again, either you know where you can look up the formula, the volume of a cylinder is pi r squared h. This is definitely going to be easier to solve for h rather than r. I don't want to have to take a square root if I can help it. So we'll just go with 1,000 divided by pi r squared is equal to h. I'll plug that in to my surface area equation. So ultimately, I'd like to minimize my surface area, 2 pi r squared plus 2 pi r times, and I'm replacing the h with 1,000 over pi r squared. I'm going to simplify that just a little bit before I take the derivative. Let's say I can call that pi's will cancel. I can call that 2,000 r to the negative first. So we'll do our first derivative test. The derivative would be 4 pi r minus 2,000 r to the negative 2. And I'd like to know where that's equal to 0. If I do a little bit of a rewrite here, 4 pi r, I'm going to move that to the other side. That would be equal to 2,000. And I'm going to go ahead and put that r squared in the denominator. And if I multiply both sides by r squared, by the way, I probably should have mentioned this last time as well. Typically, we're a little bit cautious about multiplying by a variable like that, but in this case, we know that r is not 0 because we wouldn't have a cylinder at all. So realistically, we know that we're okay. So I have 4 pi r cubed equals 2,000. R cubed would be 2,000 divided by 4 pi. And if I take the cubed root, r turns out to be approximately 5.42. And this would be in centimeters. All right. Again, I'm going to leave that check to see that it's truly a minimum up to you. But let's just go ahead and make sure we've answered. We wanted the dimensions of the can. We've got the radius. We still need the height. So to get the height, I'll plug back into my constraint. H would be 1,000 over pi times that 5.42 squared. Oops, a little dark there. And so we're coming up with about 10.84. Also in centimeters. So there are my dimensions. And I just wanted to point one thing out to you. The 5.42 is a radius, meaning the actual diameter of the can would be double that. So my height, 10.84. With the radius of 5.42, that means the diameter all the way across would be 2 times that, which is also 10.84. So the most efficient can, in terms of radius and height, or size in general, is the one in which the diameter of the base and the height are identical. Now, if you think about it, the cans that you usually see and that you might buy things in like a grocery store or something usually aren't put together this way. They're usually taller and more slender. And the reason for that is actually more of a practical reason. Many cans are meant to be held in the hand. And if you've got a can that's very wide, that's difficult to do. But if you think more about cans that aren't meant to be handheld, think about a can of paint or something like that. You might notice that in a can of paint, like a gallon of paint, it is true the diameter is very close to the height. And the reason for that is it's the most efficient. They can make the can using the least material. All right, let's look at another example. Number 8. We have 2 factories located 10 miles apart on a straight road. Their power source is on a perpendicular road, which intersects the factory road exactly halfway in between the 2 factories. The power source is 8 miles away from the intersection point. How should the power lines be run so that the total length of the lines supplying the 2 factories is a minimum? So again, let's start with a picture. I have 2 factories located 10 miles apart on a straight road. I'm just going to call them F1 and F2 just so I can refer to them. And the power source is on a perpendicular road, which intersects the factory road halfway between these factories. So exactly halfway in between here, we've got a road up perpendicular, and that's the power source P. So this is 5 and this is 5. My goal is, one more thing. The power source is 8 miles away from the intersection point. So that's 8. We would like to figure out how to run our power lines so that the total length of the lines is a minimum. Now notice we've got some choices, right? We could just run 2 straight lines to the 2 factories, so they each have their own individual line. Or we could run the lines together down to the intersection point and then split them. Or, the more general case, we could run the lines together for a while and then split them off, 1 to each factory. That's actually going to be my most generalizable case. And so I'm going to go with this. Eventually, we should be able to see that if one of the extremes was the solution, we can find an absolute max and min on this problem to see whether one of those would have actually been better. So here we go. We have to set this thing up. And I'm going to start by saying, just because I've done this problem, of course, many times, in problems with this type of setup, your best bet is to divide a variable x, and x is actually going to be the value of this little piece right in here, from where the power line split down to the road. So I'm going to call that x. That means that since this total road was 8 miles long, this part up here is going to be 8 minus x. Let's call the other pieces y, and say that my objective function is that I would like to minimize the length L, and the length of the power line would be this one, 8 minus x, plus 2 y's. All right, our typical issue, we got too many variables, and so I need a constraint. And this time the constraint actually isn't going to come from the problem. I've actually used all of the information I was given. The constraint this time is actually going to come from the picture. If you look at one of these triangles that's formed down here, notice that it's a right triangle, and so the Pythagorean theorem applies to it. So my constraint is actually going to be the Pythagorean theorem. 5 squared plus x squared equals y squared. And so y would be the square root of 25 plus x squared. Now usually I have to worry about the plus or minus on the square root, but again, since y is the length of a power line, I know it has to be a positive value, so I'm only going to take the positive square root. All right, that means when I substitute this back in, my objective function now says that I want to minimize the length 8 minus x plus 2 times the square root of 25 plus x squared. We'll do our first derivative test. L prime would be 0 minus 1 plus, if I rewrite that square root as 1/2 power, 1/2 times 2 would just be 1, times 25 plus x squared to the negative 1/2, and then times 2x for the chain rule. And again, I would like to know where that's equal to 0. So I'm going to do a little rewriting as I move this 1 to the other side. This would actually be 2x over that square root. And again, I'm going to add the 1 over to move it to the right. So if I multiply both sides by that square root, 2x will equal the square root of 25 plus x squared. And we'll square both sides. Four x squared equals 25 plus x squared. So 3x squared equals 25. And x would be square root of 25 thirds, or approximately 2 point, let's call it 2.9. I'm going to round to just one decimal place this time. And that would be miles. So the critical value here would be to have this little piece x be 2.9 miles, meaning we'd have, what, 5.1 miles that we'd come down straight, before we'd split off in both directions. Now, that may truly be the minimum, and we'll find out. But this is a situation in which we actually have some endpoints. It's not possible for x to be absolutely anything. In fact, the smallest x could be a 0. That would be the case where we come straight down to the 2 factories from p. And the largest x would be 8, right? If we come all the way down and then split. So let's test this time using our technique for testing for an absolute max-min. We know x has to be in the interval from 0 to 8. No other choices. And so I'm going to say 0 and 8, the endpoints would be included, as would the 2.9. If I now put my original function for L in my calculator, it was 8 minus x plus 2 times the square root of 25 plus x squared. And go to my table. I can see that, let's see here, 0 gave me 18, 2.9 gave me 16.7, and 8 gave me 18.9. So seeing this, I can now pick this out. This truly is the absolute minimum value. And notice I treated this one a little bit differently. Rather than doing that test that we were doing earlier, right, where we just go ahead and check the sign of the derivative to see whether we have a max or a min. In this case, because I had a very specific range of values that x was allowed to be, I used the absolute max-min test to show that I really did have an absolute minimum. As far as how should the power lines be run, I guess on this one maybe I just give it as a description. Again, if you think back at the original problem, if x was 2.9, then 8 minus x would be 5.1. So what we could say is we're going to run the line 5.1 miles before splitting to the 2 factories, or some kind of description like that. So we'll say we'll run the power line along the road, 5.1 miles, then separate to each factory. Or anything reasonable that describes the situation would be fine. All right, let's look at another one that's somewhat similar in its setup. Number 9, we have an offshore oil well, is 2 kilometers off the coast. The refinery is 4 kilometers down the coast. Building a pipeline in the ocean is twice as expensive as building it on land. What path should the pipe follow in order to minimize the, oops, that should be cost. Not much we can do about the coast, right? All right, so let's see what we've got here. Let's say this is our shoreline right here. And the oil well is 2 kilometers, W for well, off the coast. Additionally, there's a refinery 4 kilometers down the coast. So this is my refinery R. And I would like to know how to build the pipeline in order to get for the least cost so that I can take the oil from the well to the refinery. Now we have a very similar type of choice to make as we did last time, right? We could go straight from the well to the refinery, but then we're all underwater. So it's the most expensive type of pipeline to run. We could go straight to shore and then over, but that's the longest distance. The most general case would be to go underwater for a while and then at some point we'll hit the shoreline and finish on land. All right, so let's set it up that way. I'm going to once again say this little piece here, let me call that x. And that means that the pipe that's on the land here would be 4 minus x. For right now, I'll call the pipe that's underwater y. And I'm going to say that my objective function, I would like to minimize cost. And the cost, since it's twice as expensive to run the pipeline under the water, I'm going to say the cost would be double y plus 4 minus x. Again, I doubled that one only because it was twice as expensive. By the way, this isn't a real cost function, notice. I don't really know how much it costs in each case. I mean, maybe this is, $50,000 a kilometer, and this is $25,000 a kilometer. I don't know that. All I know is relative to one another, this is twice as expensive as that. That should be enough to figure out how to minimize. It won't give me the actual cost, but it's kind of a pseudo cost, if you will. All right, we have two variables again, and we're going to use the same type of constraint as we did last time. There's no more information in the problem, but I do have this right triangle here. And in that right triangle, I can use a Pythagorean theorem. X squared plus 2 squared equals y squared. So y would be the square root of x squared plus 4. Again, I'm not worrying about the negative square root since y is a distance. It can't be negative. And so my goal now becomes to minimize the cost function, which when I plug this in here becomes 2 times the y, which is now square root of x squared plus 4 minus x. So we're going to do a first derivative test here. C prime, once again I'm going to say instead of a square root, let's think of that as a 1/2 power. So a half times 2 would be 1 times x squared plus 4 to the negative 1/2. And then my chain rule gives me a times 2x there. And then I've got a plus 0 and a minus 1. And I'd like to know when that's going to be 0. So this first term is really 2x divided by the square root of x squared plus 4. And I'll add the 1 over, so that's equal to 1. And then we'll just multiply both sides by the square root. So 2x is equal to the square root of x squared plus 4. I think the algebra is starting to look a lot like last time, right? Square both sides. 4x squared equals x squared plus 4. So 3x squared is 4. And x would be the square root of 4/3. Or approximately 1.15. And this is in kilometers. All right, that's the x value. It's not the actual path, so I won't say it's a final answer. We'll describe later. But once again, we've got a similar situation. We can't actually have x being anything. In fact, x is a piece of this 4-kilometer distance. So if x were 0, we'd be coming straight down. And if x were 4, we'd be going all in the water. And we should test those two extremes and say, this is only going to be valid for x's between 0 and 4. So let's check the costs at the endpoints, 0 and 4, as well as at the critical value that we found, 1.15. I'll put my cost function in. See, our cost function was actually 2 times the square root of x squared plus 4 minus x. And I wanted to check 0, 1.15, and 4. And so there are my values. 0, my pseudo cost is 8. 1.15, I get 7.46. And at 4, it was 8.94. So once again, I've now numerically verified that the smallest cost really is right there for x is 1.15. And so, let's see, if I have to describe this, if x turned out to be 1.15, then 4 minus x would be 2.85. So what we could say is that we're going to run the pipeline underwater, and then we're going to hit a point 2.85 kilometers rather, from the refinery. So we'll say, let's run this pipeline underwater to a point 2.85 kilometers from the refinery, and then build the rest on land. And again, it just sort of said how to do this, so it's any description that describes how to build the pipeline would be fine. All right, we will pause there and come back and finish the last few examples in our last video for this section.